If your gravity feels like a gentle, reassuring hug, you're on Earth. It's the force that keeps our feet on the ground, a constant, familiar presence we rarely even think about. It's just there. But what if gravity wasn't so gentle? What if, instead of a hug, it was an inescapable, all-crushing vice? Imagine falling toward one of the most extreme objects in the universe. An object so dense, so powerful, that it bends the laws of physics to their breaking point. If your gravity squeezes you into a pancake, you're a neutron star victim. If your skin stretches like taffy, you're not landing. You're history. This isn't a gentle descent. This is a one-way trip into cosmic oblivion. So, what exactly is this celestial monster, and what would really happen if you fell into one? Let's start with the basics. A neutron star is the collapsed core of a massive star that has gone supernova. It is, in essence, a stellar corpse. But this is no ordinary remnant. A neutron star packs the mass of about 1.5 times our Sun into a ball just 20 kilometers or 12 miles across. Imagine taking our entire Sun and crushing it down until it could fit inside a major city. The result is an object of almost unimaginable density. A single teaspoon of neutron star material would weigh about 6 billion tons, as much as Mount Everest. How does such an object come to be? It begins with a star much larger than our Sun, at least 8 times its mass. For millions of years, this star fuses lighter elements into heavier ones in its core, releasing a tremendous amount of energy. This outward pressure from fusion perfectly balances the inward pull of gravity, but eventually, the star runs out of fuel. With the furnace extinguished, gravity wins. The core collapses catastrophically in a fraction of a second, shrinking from the size of Earth to the size of a city. The outer layers of the star rebound off this newly formed, incredibly hard core and are blasted out into space in a spectacular explosion we call a supernova. What's left behind is the neutron star, a monument to gravity's ultimate triumph. Peeling back its layers reveals a structure stranger than any science fiction. On the outside is a crust, about 1 kilometer thick, made of a rigid lattice of atomic nuclei and a sea of electrons. It's incredibly strong, but beneath it, things get weird. The pressure becomes so immense that atomic nuclei can no longer hold their spherical shape. They are squeezed and deformed into bizarre configurations that physicists whimsically call nuclear pasta. Depending on the depth and pressure, you might find clusters of nucleons resembling gnocchi, long cylinders like spaghetti, or flat sheets like lasagna. This isn't just a quirky analogy. It's our best model for how matter behaves under such duress. Deeper still, we reach the core, a mysterious realm where even the pasta is crushed. Here we find a superfluid of neutrons, particles that move without any friction, and possibly even more exotic states of matter, like a soup of free quarks and gluons. The core of a neutron star is one of the great unsolved mysteries in physics. Now let's return to your unfortunate fall. The first thing you'd experience is the terrifying power of its gravity. Near its surface, the gravitational pull is hundreds of billions of times stronger than Earth's. But it's not the sheer strength of gravity that would kill you first. It's the difference in its pull across your body. These are called tidal forces. As you fall feet first, the gravity pulling on your feet is exponentially stronger than the gravity pulling on your head. This differential would stretch you, a process gruesomely known as spaghettification. Your body would be pulled apart with a force that no material could withstand. Your bones would elongate and snap. Your tissues would tear. The very molecules that make you up would be ripped from one another. You wouldn't even make it to the surface. Long before you got there, you would be transformed from a complex biological organism into a thin, glowing stream of dissociated atoms and subatomic particles, spiraling down to meet the star. And what happens to that stream of particles? It slams into the star's atmosphere at nearly the speed of light. The pressures and temperatures are so extreme that the fundamental structure of your atoms is destroyed. In the star's crust and outer layers, the immense pressure overcomes the force that keeps electrons orbiting atomic nuclei. Electrons are crushed into protons, merging to form neutrons and releasing a flood of neutrinos. This process, called electron capture, is what gives a neutron star its name. Your matter would be converted into the very substance of the star itself. You would literally become part of it. As if the gravity wasn't enough, many neutron stars have another terrifying feature: magnetic fields. As the star's core collapses, its original magnetic field is concentrated, becoming quadrillions of times stronger than Earth's. Some neutron stars, called magnetars, have the most powerful magnetic fields known in the universe. If you were to get within 1,000 kilometers of a magnetar, its magnetic field would distort the electron clouds of your atoms, tearing you apart molecule by molecule. It's a death by magnetism, even before the tidal forces could get you. So how do we know any of this? We can't visit a neutron star, but we can observe them. Many spin incredibly fast, a consequence of conserving angular momentum during their collapse, like an ice skater pulling in their arms. If their magnetic poles are misaligned with their rotational axis, they can sweep beams of radiation across space. If one of these beams happens to cross our line of sight, we see a regular pulse of energy. We call these objects pulsars. They are cosmic lighthouses, blinking with a precision that rivals atomic clocks, telling us of the extreme physics at play. We also detect them through the X-rays and gamma rays emitted from their scorching hot surfaces, and by the way, their immense gravity warps space-time, creating gravitational waves. This brings up a common question. What's the difference between a neutron star and a black hole? Both are born from the death of massive stars, but there's a crucial dividing line. For a neutron star, the core collapse is halted by something called neutron degeneracy pressure, a quantum mechanical rule that prevents neutrons from being packed too tightly together. But if the original star's core is too massive, roughly more than 3 times the mass of our Sun, even this pressure fails. Gravity wins completely, and the core collapses indefinitely into a singularity, a point of infinite density. This creates a black hole, an object with gravity so strong that not even light can escape its event horizon. A neutron star is the last stop on the line. It's the densest object you can have that still has a surface you could, in theory, touch. A black hole is what lies beyond that limit. So, to recap our journey, you fall toward a city-sized sphere containing the mass of a sun. The tidal forces spaghettify you, stretching your body into a stream of atoms. This stream slams into the star, where unimaginable pressure crushes your atoms, forcing electrons into protons to create neutrons. Your constituent matter is assimilated, becoming one with a bizarre fluid of nuclear pasta and a superfluid neutron core. You'd vanish into the core's weird quantum soup, where our everyday rules of physics completely break down. The short version? A neutron star is a beautiful, fascinating cosmic object that pushes our understanding of the universe to its limits. But it is a terrible, terrible place to fall.